We're going to have a quick look at how to calculate Kp using information that you might get given in the question. So this one's a really straightforward question involving the reaction of ethene and steam making ethanol, and I'd like you to press pause and have a go. Right, so if we work out the total moles, that's our first job, then we can see that we've got 155 moles of gas as our total moles, and then we need to work out our mole fractions. So we can see that if we do 95 over 155, we get 0.61, and that's for the ethene. 55 over 155 would give us 0.35 as our mole fraction, and 5 over 155 gives us 0.03 as our mole fraction. So then if we know the mole fraction, we can then work out the partial pressure for each of the reactants or products. So for the ethene, we do our mole fraction, so 95 times the total pressure, which was 60 atmospheres. So 95 over 155 times 60 is going to be 36.8. And then if we do the 55 over 155, or the 0.35 times 60, is going to give us 21.3. And again, if we do for the ethanol, we've got our 0.03 times 60 is going to come out as 1.9. If I add those all up, they should add up to 60 atmospheres, because all I'm doing is I'm working out what fraction of the 60 atmospheres comes from each of the different gases. So now to calculate Kp, this is quite straightforward. I'm just going to write my expression first. So Kp is equal to the partial pressure of the ethanol divided by the partial pressure of the ethene times the partial pressure of the water. As I said, really straightforward example. There's no molar values to raise anything to the power of, so nice and straightforward. And then we're just going to plug in the numbers that we've worked out for our partial pressures. So it's going to be 1.9 divided by 36.8 times 21.3. And that should come out as 2.42 times 10 to the minus 3. Just need to quickly work out the units. So we've got atmospheres on the top divided by 2 lots of atmospheres on the bottom. So one cancels out on the top and the bottom, so we end up with atmospheres to the minus 1. So it's going to be 2.42 times 10 to the minus 3 atmospheres to the minus 1. So this time we're going to look at a slightly more complicated example. It's the Haber process, and I'd like you again to press pause and have a go yourself at working through how to calculate Kp. Okay, so if I have a go at this, I'm going to write out, so I've got my reactants and my products. And the first thing I'm going to need to do is an ICE table, because it hasn't told me what the equilibrium concentrations of everything are. It's told me some initial values and an equilibrium value. So I can see at the start I've got 10 moles of hydrogen and 5 moles of nitrogen. And at equilibrium, there are 3 moles of ammonia. So this means that at the beginning, initially, there was 0 moles of ammonia. So I know that the ammonia has gone up by plus 3. Now this is 2 moles, so the nitrogen must have got changed by half the amount, because it's only 1 mole. So that 5 is going to go down by minus 1.5, and there's 3 lots of hydrogen, which means I've got 3 times 1.5, so 4.5. So that 10 has gone down by minus 4.5. So now I can work out my equilibrium values for all of them. So if I do 10, take away 4.5, I get 5.5. 5 minus 1.5 is 3.5. Okay, let's work out our total moles at equilibrium. So we've got 5.5 plus 3.5 plus 3 is going to come out as 12. So now I need to work out my mole fractions so that I can work out the partial pressures. So let's think about mole fractions. They're all out of 12. So the hydrogen is going to be 5.5/12. And the nitrogen is going to be 3.5/12. And the ammonia is going to be 3/12. Now I'm going to leave those as fractions for now. And then to work out the partial pressures, I know that my total pressure is 2 times 10 to the 7. So my partial pressure is going to be 5.5/12 times 2 times 10 to the 7. So that comes out as 9.17 times 10 to the 6. And then the nitrogen is going to be 3.5/12 times 2 times 10 to the 7. So that's 5.83 times 10 to the 6. And the ammonia is going to be 3/12, again, times 2 times 10 to the 7. So that's going to come out at exactly 5 times 10 to the 6. Okay, made that a bit smaller to give myself some space. So now we need to work out Kp. So if we write out the expression first of all, so let's remember it's product, so partial pressure of the ammonia. And the ammonia needs to be squared because there's 2 of them in the equation, divided by the partial pressure of hydrogen, which is going to need to be cubed because there's 3 of them in the equation, and times the partial pressure of the nitrogen. Now, if we just consider what the units are going to be at the very end, we've got pascals squared on the top, and on the bottom we've got pascals cubed times pascals, so that's pascals to the 4. So if I've got 2 on the top and 4 on the bottom, then overall 2 is going to cancel out. I'm going to get left with pascals to the -2. Now if I plug in my numbers from my ICE table and where I've worked out the partial pressures, I should be able to work out a value for Kp. So let's fill these values in. So we're going to put 5 times 10 to the 6 squared on the top. And we're going to divide that by 9.17 times 10 to the 6 cubed. And we're going to times that by 5.83 times 10 to the 6. I plug all that into my calculator. I'm going to come out at an answer of 5.56, and that's going to be times 10 to the -15. And we've already worked out our units are pascals to the -2. Okay, the next thing I want you to do then is to look at the effect of if I increase the pressure or increase the temperature. So again, press pause and have a think about what you think the effect will be on both the position of equilibrium and on Kp. Okay, so let's think about this. If we increase the pressure, we're going to move it to the side with the fewest number of moles of gas, which in the case of the Haber process is the right-hand side, the side of the ammonia. So we're going to move, if we increase the pressure, the position of equilibrium is going to move to the right. Okay, but what's going to happen to Kp? Well, Kp is a constant at any given temperature, so Kp will not change because the concentrations and the partial pressures will change in such a way that they would lead to Kp staying the same as long as the temperature stays the same. So if we increase the temperature, let's think about this, the forwards reaction is -76 kilojoules per mole. So that means our forwards reaction is exothermic. So if we increase the temperature, our position of equilibrium is going to move in the direction of endothermic change. It's going to favour the endothermic reaction, which means if we increase the temperature, the position of equilibrium is going to move to the left-hand side. Now, if we change the temperature, then the value of Kp will change. So if Kp, if we think about it, if our equilibrium moves to the left, then we're increasing the proportion of the thing that goes on the bottom, so our denominator in our fraction. So if we're increasing what's on the bottom, then our value of Kp is going to decrease. Okay, have a go at the other examples on the sheets and let me know how you get on.